when the giant star can retain its mantle, then begins the synthesis of the average nuclides up to the elements 30 such as gallium. This new stellar phase proceeds from the synthesis of billiards, with encounters and shocks of nuclides. But this time, instead of being limited to producing only helium-4, the nuclei will then agglutinate and unite to build larger and larger nuclides. Because these new carbon and oxygen cores are very strong and resistant to radiation, they will therefore serve as a basic foundation for the formation of larger nuclides. And to do that, we still have the same small transition elements like neutron, proton, deuterium, tritium and helium-3. They will thus come to integrate in the hollows of the nuclear wall by adding new pentagons and successive layers. And to describe them we begin by presenting the basic pentamorphic structures. The first morphological basis is the tetrahedron represented by carbon-12. The second base is the hexahedron represented by nitrogen-14.
The third base is the octahedron shown by oxygen-16. And the fourth base is the decahedron interpreted by oxygen-18.
But first, let us describe the isotopes of carbon to establish some general rules. The pentagons of the wall are distributed over 4 lobes positioned on the 4 peaks of the tetrahedron. Like all nuclides of medium mass, there may be gaps in the wall of the nuclides. However, since the wall is now somewhat deformed, there is no longer the stability of helium-3 or lithium-6 and 7. These lacunar isotopes are therefore unstable, with, for example, a life duration of 20 minutes for carbon-11 and 19 seconds for carbon-10. Of course, in the mantle of the star, these parietal gaps will let in the radiations, and the nuclide will disintegrate. Similarly, heavy isotopes with external helices remain as unstable as helium-6 or 8, as is the case with carbon-16, with half-lives of less than 1 second. These external propellers are blown rapidly, leaving the wall of the core completely stripped. On the contrary, the more the volume of the nuclide will increase and the more flexible the wall will become, and thus, the heavier nuclides will be able to integrate more and more internal pentagons. In the case of carbon-13, the suppleness of the wall makes it possible to integrate 3 additional pentagons in the form of an entire dodecahedron on one lobe, while the tension is distributed over the other 3 lobes. But the limit of flexibility is reached with the carbon-14, which integrates 6 internal pentagons in the form of central deuterium. It has a half-life of about 5,700 years, and its 6 internal pentagons will emerge in a new lobe to give nitrogen-14. But we can observe again the effects of pentamorphism in the sense that carbon-12 and carbon-14 have a spin of 0, which shows perfect symmetry. And conversely, carbon-13 shows a half-spin, and thus an asymmetry linked to the fact that one lobe is heavier than the other 3. Hence, after proton and helium-3, carbon-13 is the first asymmetric stable nucleus. Now, with nitrogen, we can find the same effects of restricted flexibility for the arrangement of the inner pentagons. With 6 times 7, or 42 pentagons on the outer wall, nitrogen-14 is also the base of the hexahedral structure. And like carbon, nitrogen develops a stable heavy isotope with a complete dodecahedron at one of its poles. And just as for carbon-13, the nitrogen-15 also has a non-zero spin, and therefore a clear asymmetry.
It is noted that the nitrogen-15 could have a symmetrical isomers with the central internal helix as for beryllium-9.
But this confirms the strong domination of the dodecahedron in the pentamorphic nuclear structure. On the other hand, with 2 dodecahedrons at the poles, nitrogen-16 is unstable, which shows the limits of tension of the nuclear wall at its equator. And let us also mention another very unstable isomass of nitrogen-16 with propellers at the poles. With 8 times 6 pentagons, and thus 48 pentagons on the outer wall, oxygen has 3 stable isotopes, showing greater flexibility due to the increase in size. Oxygen-16 is the isotope without internal pentagons, and its zero spin comes from its quasi-symmetric form close to the octahedron, of which it is the morphological basis. The oxygen-17 is of the same type as the carbon-13, and the nitrogen-15 with a complete dodecahedron, which provides a non-zero spin, manifesting a clear asymmetry.
But before proceeding with the elements higher than oxygen, let us present some important rules concerning the growth of the nuclides on the first parietal layers.